Today, I want to finish first bargaining, which we started. How do humans bargain when they're talking? When I'm talking to someone, we bargain, and that person talks to other people, and there's like a network. It's like sociology. Okay? So I'm going to talk first about that, and then I'll talk about the World Wide Web, and how that, so that more goes into the second part, more graph kind of part. Negotiations, a general framework. So remember, let me just refresh your memory. Just going back to an example. So we have this network here. Each of these nodes is a human, and they will bargain with each other. And the model, we will define a simple model, which is called network exchange model. And the idea is that on each edge, there is $1, or €1 if you want. And the nodes will try to come to agreement. So here, for example, A and B agree to split the dollar. A gets 30 cents, B gets 70 cents, and C is left out. Okay, which is too bad. And here D and E also split. So in this particular negotiation, A, B, D, and E get some money, but C is left out. But maybe C tried, C was talking with B, but somehow B decided to go with A. Okay? And so people talk, and eventually they agree on some kind of a partition of the money. Okay? And there's a notion of power. Let me show you another example. Just to refresh. So here, for example, let's say we have 4 nodes, and they all argue. So A can only talk to B. B talks to both A and C, but it can only agree with one of them. They make one agreement. So B has to decide which one. So B is discussing with A, and B is also discussing with C. So B has more power than A, because B can threaten A by saying, hey, I will leave you and I will go with C, and you get nothing. And A, so A will decide maybe to get less. But C can do the same with B. C can say to B, I will go with D. So B does not have infinite power. B has a little bit more power, but not infinite, because C has also an alternative. So you see the kind of psychology that's going on there. And what we want to do now is a mathematical model that kind of fits how humans will do this. So the numbers here is what happens when you real experiment with human beings, and they talk, and A will get 37.5 cents, and B will get 62.5 cents on average. Okay? But in 3 node, B has much more power, because C also has no alternative. Okay? So A will get less, so he only gets 17 cents. So now what we're going to do today is make a theory of that. Trying to figure it out. A general framework. Up to now, we have informal motivation. We kind of see how it works. If you have alternatives, and there's some notion of fairness the humans are discussing. So what I'm going to show you now is a model that actually explains pretty well how real humans negotiate on network. And the model is called Theory of Balanced Outcomes. And in order to explain this, there's actually 3 parts that I explain separately. There's Nash bargaining solution, ultimatum game, stable outcomes. And when you combine them, you get the theory of balanced outcomes. So this is the current best theory of how humans negotiate. So it's maybe not completely true, but it actually fits pretty well with how humans negotiate. So it's kind of not just mathematical, there's some sociology here. With theory of balanced outcomes, we can approximate results of human negotiations. If the human talks to different partners, we can figure out who has power. So Zelensky is talking to Putin, or somehow they're in a power situation. But Putin has another person called Lukashenko, who is the head of Belarus, and Putin is in very strong position with respect to Lukashenko, but he's in less strong position with respect to Zelensky. And Zelensky has a choice: either go with Russia or Europe. So it's a network, you see. Zelensky is like a node in the middle, and there's one possibility, another one. And so it's a whole dynamic, which is playing today, the whole Ukraine situation. And that kind of thing, you can model it with this theory. Okay, so what I'm going to show you now is the three pieces, and then we make this theory. And this one is very practical, and it can help you when you negotiate. So first step is what's called Nash bargaining solution. This is like a primitive, what happens when two people. So the single edge is like the primitive thing, when you have a network. So the first step is looking at two people. And what we want to do is we want to connect this edge with the rest of the network. This edge is a part of a big network. So there's $1 on this edge, and A and B are negotiating. But A and B have some power. And how do we model that? Well, A maybe can choose somebody else who's on the left, which I don't show, but there might be other people. B can choose somebody else. And depending how strong this one is, this makes the situation of A stronger or weaker. Okay? So basically, the power of A compared to B depends on the rest of the network. You see kind of intuition, So how do we make this precise? Well, we could say A has an outside option, X. So let's say if A decides to go outside, then he gets $0.5. So the outside option is 0.5. Okay? That means A will only go with B if he gets more than that. Okay? But maybe B has an outside option of 25 cents. So B knows for sure they can get 25 cents here. That means B will only go with A if he or she gets more than 25 cents. Okay? So B has more incentive, but A is in a stronger position. You see? So we have this idea of outside option, which is basically the rest of the network. Okay? So if A does not like his share with B, A can always fall back on X. And B can always fall back on Y. Okay? So we can assume X plus Y is less than or equal to 1, or else no way A and B are going to go together, because they will immediately go for X and Y and they will never agree, because it will always be less. Okay? If X plus Y is greater than 1, then A and B, they're going to clearly only go to the outside. Okay? So assume X plus Y is less than 1 or equal to 1. That means maybe they can still agree. But A will ask for at least X, and B will ask for at least 1. And A knows they will not accept less than X. Okay, from B, and B will not accept less than Y. So actually, A wants to get more than X, okay, and B wants to get more than Y. So the real negotiation is splitting what's called the surplus. So if you take X plus Y, 1 minus X plus Y, that's how much extra there is if they go with each other. You see that? So if this is 25 cents and 50 cents, there is 25 cents extra. Maybe A can get a little bit more, or B can get a little bit more. So there's like a pot of 25 cents to split, okay? Which is 1 minus X minus Y. So how do they split the pot? Well, we assume they will split it perfectly in half. Because somehow they will discuss, and somehow they will not, A will not agree for less anything else, and B neither. So A will get x plus s over 2, and B gets y plus s over 2. You see, so if they go with each other, they get a little bit more than the outside. How much more? Well, it depends on what the pot is, what the extra is. So if you simplify this, you get here this solution. A gets x plus 1 minus y over 2, B gets y plus 1 minus x over 2. This is called the Nash bargaining solution, because it's kind of an equilibrium between A and B, yeah? A will not agree for less, B will not agree for less, so they split in half, okay? So this is how A and B, we predict that's what they will do if they have outside option, okay? So this is the first part. It's called the Nash bargaining solution. So when we have a big network with many links, each link will have its own little Nash solution. You see? They're kind of splitting the pot. So that's the first part. The second part is called ultimatum game. So it's between two people. But now we're talking about extreme situation. Extreme, when you have really going to the edge. Okay? Because humans don't like the extremes. So this is kind of sociology. So let's say you have A and B, and they're negotiating. And here's the idea. This is called ultimatum game. A has $1, and A proposes to give something to B. So A will keep part of the dollar. Let's say $1 million to make it more interesting. Okay, A has $1 million, and A proposes, says, I will give 100,000 to B, and I will keep 900,000. So A makes the proposal, and B has an option then, accept or reject. And B says, I'm getting 100,000, that's nice. Okay, I accept. So that's it. That's the whole game. A makes the proposal, and B says, I accept or I don't. So if B doesn't accept, then they get 0. Both get 0. So according to game theory, B should accept any amount bigger than 0. Huh? Even if A gives $1 out of $1 million to B, well, it's better than nothing, right? So B should accept. But humans are not going to do like that. Huh? I would be very insulted if A is getting 1 million and A only gives me $1, okay? I would say, no way, I'm not agreeing to that. Humans don't like extremes, okay? Humans don't do like that. Humans are not going to accept extreme. So what if you do it with real humans? You give A $1,000, A makes the proposal. A says, I give $1 to B, and I keep 999. B is going to say, that's pretty insulting. No, I reject. So everybody gets 0. So A has to give more to B, so that B is not insulted. Okay? So there's what's called an emotional payoff. For humans, they don't want to feel they're being cheated. You see the idea? So A is getting a lot of money, and B wants some kind of share of that. And not $1, okay? In real life, it's usually fairly balanced. If A has $1,000, usually B will only say yes if they get like 1/3 of that. They will allow A to get a little bit more because A has the pot, but it has to be kind of fair. Okay, so it's usually fairly balanced. So humans do not think like pure game theory because there's an emotional thing attached. If B gets a low offer, B is going to be very happy to reject it. See how that works? So the conclusion, humans will not go to extremes. They will not split extreme balances very widely. They tend to be more balanced. Okay? So if we have a theoretical model that gives extremes, the humans are not going to behave like that. They're going to be more balanced. Okay? So this is called the ultimatum game, and so humans tend to be more balanced. So that's the second thing. Huh? So the first was the Nash, where they split the pot. Here the second is no extremes. And the third one is called stable outcomes. So this is about stealing negotiation. Okay? Stable outcomes. So we have a big network, and the nodes agree on something. Okay? And there's kind of there's a matching. Okay? So let me show maybe an example. Get a piece of chalk. So we have something like this. Let's say we have this kind of network, A, B, C, and they will negotiate. Okay? And some point, there's going to be a matching. Okay? For example, A will agree with B, and C is left out. So we have a matching. Yeah? Remember we talked about matching. Huh? And then there's a number. So maybe A will get 50 cents and B gets 50 cents. For example, this is how much each node gets, and C gets 0, for example. Now, we can ask a question on this. Is it stable? Stable means, can a node steal negotiation? So here, for example, A and B split $1, and B gets 50 cents. But C can be smart, and C knows that there's $1 to be split here. So C can tell B, if you go with me, I will give you 60 cents, and I will take only 40. So C can steal the negotiation from A. So B says, oh yeah, sure, I want more. So B will go with C. So you see, C can steal the negotiation. You see how it works? Question?
Yes, but won't it be basically a cat and mouse game where A will be like, I can give you points?
Yes. So if B steals, maybe A can steal in the other direction. So then it's not stable either. So eventually, there's some kind of a situation when nobody can steal anymore. Yeah, so if C steals from B, then we get this. Then we get this situation where C gets 0.4, B gets 0.6, and A gets 0. But now A can do the same, of course. A can say, hey, come with me, and you'll get 0.7. And I will get 0.3, which is better than 0, and C will get 0. So again, A can steal now. So the first one is not stable because C can steal. But the second one is not stable either because A can steal. And this will keep going until nobody can steal. So what's the limit? What will happen? How can you make it so nobody steals? There's not so much, there's some kind of extreme limit that's going to happen, huh? See that? So here's a bunch of examples. So here, the top left one, ABC, 1/2, 1/2, 0. So this is the one we had here. And C can steal and offer a little bit more. But then A can steal. So this is still unstable. And A can steal. But eventually it's going to reach limit when nobody can steal. So if you look at the top right, 0, 1, 0, C cannot offer more because there's only $1, you see? So this one on the left is unstable because C can offer B more than 1/2. But if B accepts that, if this is like 0.6, then again A can steal. So it's going to like there's going to be like a race up to the limit. And then we get to the situation here. B gets 1, and both A and C get 0. Well, C can no longer steal because C cannot offer more to B. Okay? C cannot offer more. So this one is called a stable outcome. Of course, it's not the one humans are going to choose, of course, because A is getting 0, and A would never agree on getting 0. So this is not what humans would do, but it's a technical concept, stability. C cannot cheat, or steal the negotiation, because C cannot offer more to B. But what about this one here? 1/2, 1/2. So these two agree, and here 1/4, 3/4. Is this one stable? What do you think? For example, could C make a higher offer to B? Yeah. Well, C is getting 1/4. So C wants to get more than 1/4, but C wants to get more than 1/4. Okay. Well, C could offer a little bit more than 1/4 and offer B a little bit more than 1/2, right? C could offer 3/8 for himself and 5/8 for B and steal B from A. See that? So this one is not stable because C can steal. Okay? C can steal B and get more money. What about B? Can B steal from C? Could B make a better offer to C than 1/4 and still keep at least more than 1/2? Is it possible?
Yes.
Yes, If B says, I take 5/8 and I give 3/8 to C, then C's advantage is to go with B, of course, So B can steal C from B. Okay? So this one is not stable because they can do stealing. Okay? What about the one on the right? Is it stable or not? Can C steal from B? I'm talking about this one now. Can C steal from B? What do you think? Could C offer more than 1/2 to B and still get at least 1/2 itself? No, because there's only $1 to split. So basically, C cannot steal. Because there's no way C can offer more. It would get less, so it's not going to do it. C's not going to do that. So the one on the right is stable. Okay? But it's not maybe the only one. What about the one on the bottom? Is this one stable or not? Can C steal from B? What do you think? Can C give more than 2/3 to B and itself give at least no, because the sum of those two is bigger than 1. So if C gives more than 2/3 to B, there's nothing left over. So this one is also stable. So you see, stability does not fix the numbers. It's just like a constraint. It's like there's no cheating, it's like a constraint. You see? Some are stable, some are unstable. Okay, so I kind of gave you the solution, but you should work it out also by yourself. Okay, so what's the theory of that? What's the mathematical condition that you can steal or not? So let's take a look. So there's actually a very simple mathematical condition. So on the left, 1/2, 1/2, and then 0. This is unstable because C can offer 2/3 and keep 1/3. And here on the right, it's stable. C can offer nothing. Cannot offer more than 1. Okay? So the outcomes that really happen in practice should be stable, of course. See, this is kind of humans will take advantage of stealing the negotiation. course. So human outcomes will be stable, of course. Sabotaging the agreement, humans will do that, of course, if they can get more money. So any agreement that humans do has to be stable from this argument. So the condition is actually very simple. If Y wants to steal from X, then the sum of the two has to be less than 1. So here we have 1/2 plus 0, which is 1/2, and that gives you how much less than 1. So that means there's 1/2 left over, okay? 1/2 that C can split between the two, or they will both go higher. You see that? So 1/2 and 0, so there's 1/2 left over. So C could say 3/4 for B and 1/4 for me. So it's splitting that surplus half into 2/4. So the condition is that every edge not in the matching has to have a sum less than 1. Okay? That's instability. So in order for there to be stable, this should never happen. You should never have that the edges not in the matching have a surplus. Okay? If the sum is less than 1, then there's a surplus. And C has some leverage. See that? Okay? So that's the third notion, the stability. Okay? So stable outcomes that humans do for an outcome not to have the opportunity for two nodes to sabotage or disrupt, it has to be stable. So the outcome is stable if there's no instabilities. There's no way for a node to steal a negotiation. Okay? So humans, we expect this, of course, if we're humans. So stable outcomes, they capture something of humans. Okay? Okay? This, you see, you have to combine it with the extreme imbalances. So humans will never go to 0, 1, but they maybe will go to 1, 6, 5, 6. Okay. Also, if you look at the freestanding triangle, remember the triangle? We have this triangle, A, B, C. There's always a way to cheat. I mean, there's many ways to cheat. This is kind of an unstable pathological case. There's lots of instability, so you can look at that. So you should exercise, look at this, okay? Okay. So stability is not enough. So it's like a constraint, no cheating, no instability, but it's not enough to give you the whole answer, okay? It's not strong enough. So here's an example with the 4 nodes. So we showed it already before, 1/2, 1/2, 1/2, 1/2. So the first one is stable because C cannot cheat. But the second one is also stable, 1/3, 2/3, 2/3, 1/3. C can also not steal B. Because the sum of these two, it's only like an inequality, okay? It's greater than or equal to 1. So stability is not strong enough to give a full solution. There's a large range of stable outcomes here, okay? So typically, when the power balance is kind of weak, so B and C are not very strong, and the difference between B and A is not that much, so there's many possibilities for stability, okay? So in networks with small power differences, stability is not really so strong. Okay, so stability is not the whole solution. Okay, so you see now we found the 3 principles. Nash is how two nodes split the pot. And then we have ultimatum game, humans don't like extremes. And stability, there should be no way of cheating or stealing a node. If we combine them, we can come up with a theory, and this one is called the theory of balanced outcomes. So it's more than just stability, okay? So we said there's many possible stable outcomes, okay? So here's 3 examples for the 4-node network. 1/2, 1/2, 1/2, 1/2, 1/3, 2/3, 2/3, 1/3, and a third one, 1/4, 3/4, 3/4, 1/4. All of these are stable, okay? All 3 of them are stable, but they're not the same, okay? B gets 1/2, B gets 2/3, B gets 3/4. But in none of them you cannot cheat. So 3/4 plus 3/4 is 1.5, 6/4. So C cannot offer more to B, so this cannot cheat. So they're all stable. So now the question is, which one of these is going to be picked? Well now we go back to the Nash solution. Remember the Nash solution said, if you have 2 nodes, and it depends on the outside option, whatever they get if they go to the rest of the network, and they will split the pot. They will split the surplus. Which is S1 minus X plus 1. So that's the Nash solution. Well, if we apply this to the 3 stable outcomes, we can actually pick one that is, there's only one of those that fits with this. Okay? And that will be the one. So, for example, take a look at the top one. A has an outside option of 0, of course. If A does not go with B, then he gets 0. B has an outside option of 1/2. If B goes with C, then B can get 1/2. Okay? Fine. So that's not a Nash solution, this one. Let me point to it. This one is not a Nash solution because there's a surplus. The surplus is 1/2. It's the difference between these 2 and 1. So the Nash solution would say this has to be, they have to split the surplus. Okay? The Nash solution would be 1/4 and 3/4. So this is not Nash bargaining. So AB is not a Nash bargaining solution there. Okay? What about this one, the second one? So 1/3, 2/3, 2/3, 1/3. So A again has an outside option of 0. B has an outside option of 1/3. So C is getting 2/3. So C will never agree to get less. C is already getting 2/3. That's an acquired thing. So C will never agree to get less. So the only way for B to go with C is for B to accept 1/3. You see that? C is already guaranteed to get at least 2/3. So the outside option for B is 1/3. 0 and 1/3. That means the surplus, the leftover, is 1 minus this, which is 2/3, which is split between A and B. That means 2/3, so A gets 1/2, which is 1/3. B gets 1/2, which is 1/3, plus the outside option, which is 2/3, which is exactly what they get. So this one satisfies the Nash solution. Okay, and the same for CD. So the middle one is the two red lines are Nash solutions. And let's take a look at the final one now. So again, A has outside option 0, of course. B, if B agrees with C, then B will have to agree to 1/4, because C will never go less than 3/4. So the outside option for B is 1/4. So the surplus here is 3/4. See that? 1 minus the sum, 3/4. So half of that is 3/8. So that would give A 3/8, and B 3/8 plus 1/4. So 3/8, and 3/8 plus 1/4 is 5/8. 3/8, 5/8. Well, that's not what's said here. So this is not a Nash stable. Okay? These numbers are not agreeing with the Nash solution. So the only one of the three that agrees with the Nash solution is the one in the middle. Okay? So this is the one that the theory predicts. We say it's balanced because all of the red lines are Nash bargain solutions. Okay? So the middle example is the one that fits the Nash bargaining. A and B are not going to agree on anything else because of the outside options. Now remember the discussion, huh? So the only one that works is the middle one. See that? And the top and the bottom one don't work. So that's it. That's the theory of balanced outcomes. Okay? So summarizing, a balanced outcome, an outcome. So an outcome is a matching plus the numbers. It's all the red lines plus the numbers. It's balanced if for each edge the money is split according to Nash bargaining solution. So all the red lines have to be split according to Nash solution. Okay? Given the best outside options. Okay? This is it. That's it. That is the theory of balanced outcome. So B and C, the Nash solution is kind of a middle thing, huh? They will not get too little or too much because they're splitting. They're splitting a surplus, so they will actually kind of be more even. Okay? Notice it's actually recursive. If you want to compute this for a real network, then you get kind of recursive equation. Because this outside option depends on what the split is here, okay? So the values of the nodes depend on the outside option, but the outside option depend on the other nodes, and eventually it also depends on the B and C values. So there's actually, if you want to compute this, it's actually recursive equations, but they're not hard to solve. And then you can say, can you always have a solution? Well, yes, any network that has a stable outcome also has balance, so you can prove that. So we're not going to prove it, but you can prove that. Okay, so that's it. That's how humans negotiate. Okay, so they try to make it so nobody can steal. They split the surplus, and it's recursive. So everybody negotiates like that. Okay. So here's an example for balanced outcome. Remember this graph. This is what I call the stem graph. It's a triangle with a line sticking out, which is the stem. Okay. A, B, C, D. So let's take a look. A has an outside option of 0, and C and D are symmetrical. Okay, so they will each get a half. So B has an outside option of a half. It can never. It will. If it wants to go with C, then C has to get at least a half. So B can make sure it gets a half, but no more. C has an outside option of 1/4. The only way to get that is to go with B. But since B is getting 3/4, then C can only get 1/4. So the outside option is 1/4, and the same for D. So this gives numbers. And if you calculate the Nash solution, you see both of these are satisfying the Nash solution. Okay? For example, here, the surplus is 1/2. 1 minus is 2, which is 1/4, 1/4. So that means A gets 1/4, and B gets 1/2 plus 1/4, 3/4. So this is good. Here, again, the outside option is 1/4 and 1/4. So the surplus is going to be 1 minus that, which is 1/2. Okay? And that's half of that is 1/4. So 1/4 plus 1/4 gives half. Also half. So both of these are Nash bargaining solutions. Okay? So if you do real, the funny thing is, if you do real experiment with humans that are talking in this situation, that's what they agree on eventually. Isn't that funny? So this theory actually has a correspondence to how humans think. This is experimentally verified, huh? Okay? And you can compute these. So I'm not going to give you the equations for this. We could go off and I could show you how to set up the equations. But usually, with a little bit of reasoning, you can determine what are the Nash solutions, and then you can just verify that they're all satisfying the Nash bargaining solution. So conclusion, then, on the bargaining on networks. So the theory of balanced outcomes, okay? So you can compute them. It exists whenever a stable outcome exists. So a network with no stable outcomes, then you will not be you will not get any balanced outcomes. And you have networks like that. So you can have treacherous networks like the triangle, where you can always be stealing. And in real life, you can have that too. If you have three countries who are trying to go together in like a triangle situation, then, and there's no moral qualms, they will agree to whoever gives them the most, then again, it's not stable. It can always change. So that's possible. But if there does exist a stable outcome, then you can always find balance. Okay? So some networks are inherently unstable. So if you ever do real negotiation in the real world, if you're ever in this situation, maybe you're a very crafty manipulator, then you will deliberately create an unstable network so that it doesn't go to a stable solution. Or maybe you're an honest negotiator who wants to find a solution, then you will actually create a network where there is a stable solution. Okay? And as far as we know, so this is the most advanced theory, or one of the most advanced. Balanced outcomes is what humans do. It's interesting, huh? So this is corresponding to thinking processes of these weird animals called humans. But there's no proof, okay? This is kind of a hypothesis. There are other theories, which I'm not going to present, but the balanced outcome, you see, it's kind of very intuitive, and it actually corresponds pretty well. Okay? And there's more, if you want to go farther, you have to look up cooperative game theory. So this is an example of cooperative game theory. How players will divide up the value from collective activity, okay, a collection of players. So I'm not going to go into that, but this is going like in that direction, okay? So the theory of balanced outcomes. Okay, so this basically, so I'll give you a summary of the negotiation on the network. When the nodes are in the network, they will negotiate. And the power depends on where they are. Each node negotiates with its neighbors. So it's not obvious how that works. And therefore, there's researchers, they did real experiments with humans and also theoretical models. And the result is that there are three important principles were found. Nash bargaining solution, that means two participants will agree that the split is fair, in a sense that they're splitting the surplus fairly. Ultimatum game, which means they stay away from extremes. And stable outcomes is that you cannot steal. The total solution has to be the one where you cannot steal. And if you have these three, if you define a network where every edge is Nash, that's balanced. Every balanced outcome is stable, and every network that has a stable outcome has a balanced outcome. And of course, there do exist networks that have no stable outcomes. And in the real world, that gives wars that go on forever. If you have this kind of situation, like there is in the history of China, there was in the several centuries BC, there was something called the Warring States period, when over multiple centuries, it was one war after the other, Well, it was kind of an unstable situation, okay? So I don't know if anyone has formalized that in this theory, but you could possibly formalize that and show why the network is unstable. And eventually they came to a stable one, but it took centuries of change, okay? So this kind of theory really works in the real world, okay? Seems to correspond to how humans are thinking, okay? So that finishes now the part on bargaining. Before going to the break, let me take a step back and kind of give you an overview of the whole course and a theme, okay? All the examples we see, all the different examples. I remember the balance theorem, structural equilibrium, remember the trading networks, the markets, the auctions. What is the common theme? Well, there's a common theme. It's always moving toward an equilibrium. Okay? So let me give you, just to give you an idea, show you. So we saw graph theory, game theory, and the second part is game theory for markets and negotiation. That is the part that we just finished. And the next part, the final third, is graph theory for networks, like the web, information networks. So the common theme here is that in a complicated thing, like a social network, it's always changing. It's always evolving towards an equilibrium, so it's converging in a sense. Markets will converge to market clearing. Bidding, auctions will converge to bidding your true value, okay? Structural equilibrium with stability unstable will converge to n groups of mutual enemies, okay? So we give many models, and we proved things for these models. These are simplified, idealized, because the real world is very complicated, but they still hold. So these idealized models are actually very cleverly chosen, and it actually helps you for real world things, okay? And then just some examples of what we saw so far, and then that will make the break. Remember social networks first. Remember triadic closure. Friends of friends tend to become friends. That's an evolution. And the network will become denser. So the convergence is that everyone is friends. Structural equilibrium, when you have enemies, you have balanced groups of mutual enemies. In game theory, Nash equilibrium, in real games, it's locally the best. Each player cannot do better. And it's recursive, okay? But you also have global optimum. You also have global optimum, which is Pareto optimum or social optimum. This is when you have governments making regulations. So you want to maximize the global well-being, okay, the global payoff. And so the real societies are, in some sense, converging towards that. And if you're smart, if you do free markets, then the selfish solutions will also be socially good. That's actually the best if you can achieve that. So the third part was auctions and what we saw in markets. Remember the second price auction? Bidders tend to bid their true values. That's the optimum. Or market clear. The prices will fluctuate, but it will converge so that everyone is happy, and this actually gives you social optimum. Or trader equilibrium. If you have traders, you converge toward stable payoffs. You might have competition or monopoly, but it depends on the topology. And the thing we saw last week and today, so you reduce instability. Ability for a node to sabotage, and everybody tries to get a locally fair solution, which is the Nash solution. So it's all kind of converging toward equilibrium. You see, that's kind of the theme, huh? Okay. Okay? That theme will continue in the last third of the course, but now we're going to talk more about the graphs, the large graphs. Okay? So now the part where it's really focused on game theory has ended. And now the last third of the course, it's going to be more colored into graph theory. And the first thing we're going to look at is the World Wide Web. But let me first make a break. The last third of the course, where it's more colored in terms of graphs, a little bit less in terms of games, but still the same kind of principles. The graphs are evolving, you want to understand what's going on. The first part of this is going to be discussing the World Wide Web. So the World Wide Web is a very important thing. It's an information network. And since also now people are since some years doing business on it, it's also an economic network, and it's overlaid on the internet. So it's basically like an overlay. It's kind of like a social network. It's fully decentralized, so there's no centralized control of it anywhere. Okay, so we will explain that. And it has a global structure. So it's very interesting to see what the global structure is. I mentioned it already in the very first course, but we're going to go more into that, the bow tie. And it's huge. And the problem is, how do you search information? It's very hard if there's billions and billions of pages. And the first company who solved this problem in the 1990s became very, very rich with this solution. They were the first ones, and they are called Google. And they invented the first algorithm that was really able to solve this, called PageRank. So we'll explain how it works. And the web continues to evolve. So there's Web 2.0, but now there's even a Web 3. People talk about Web 3.0, and there's targeted advertising, adversarial problems where people are trying to cheat and get higher links on the search engines. So we're going to talk about all of that. Okay? So today I want to give you the first introduction, and next week we will go more into detail on how all of that works. So first, the structure of the web. So some basic notion of how the web is structured. It's decentralized transport scalable. So each node knows neighbor nodes. There's no inherent global knowledge. It's all based on the internet protocols. So the IP and TCP protocols. It's basically built on top of TCP and DNS, the domain name system. So I'm not going to talk about those guys. Normally you saw already those guys in another course. We're going to talk about what's on top of it. And there's all the other networks, the social networks we talked about. It's all on top of the internet, the TCP, DNS. And so it's all what's called overlay networks. Facebook, Twitter, etc. They all have their networks. And so the World Wide Web is what's called a hypertext graph. So each node is like a text document that has reference to other node, and you can follow the links. So that's what's called a hypertext. And that's what we're going to study today and next week. So it's a hypertext graph. So there's two ideas there. Hypertext. Each node is a textual document called a page, and it has links to other nodes, so edges, directed edges. And so that's already hypertext. That existed already before the internet, because you could have hypertext on a single computer. It's just a way of organizing pages, where you have links between pages. The second idea is called network distribution. The pages are spread all over the world. They're not all sitting on one machine. They're geographically distributed. Okay? This was originally developed for sharing information. So the original main authors were Tim Berners-Lee, Usually it's him, he gets all the attention, but there's a second guy called Robert Caillot, and they were doing this at CERN, and this was 1989 to 91. So Tim Berners-Lee is a British citizen, and he got a knighthood, so he's called Sir Tim Berners-Lee. Robert Caillot is a Belgian. Okay, we'll see Belgium actually played a strong role, and he got something called Commandeur dans l'ordre de Léopold because of this. So these guys, but Tim Berners-Lee continued working on successors to the web, which is called semantic web, which I'm not going to talk about so much. And so what are the key features? That anybody can make web pages on your own computer. Everybody can access web pages using a software tool called a browser, navigator. It's completely decentralized. There's no central control. Anybody can make pages anywhere. And in order to make it easier, they define a new protocol called HTTP, which is essentially running on top of TCP. Okay, so that's the technical part. Before going into how to search, I want to say something about precursors. This is very important, the history. There's some really interesting history. And in fact, in the Moodle, there's two very nice documents. One is the one by Vannevar Bush on the Memex, and the other one is by Paul Aulet on the Universal Book. And these are very old, and they basically predicted the web many years ago. The first precursor is citations in scientific articles. Every scientific article, a scientific article is not like a novel. It has a bibliography and it credits earlier work. So it builds on top of earlier work. And so every article is like a hypertext. The whole thing is like a hypertext. So citations are only going into the past. When the article is written, they point to previous articles. Okay? That's almost always true. So here's, for example, some articles that are related to what we saw in this course. Cosinets, Watts, remember we saw some models. This article has references to an article by a guy named Granovetter. Remember this? There's also a guy named Milgram with Travers. Remember the 6 degrees of freedom? So this article references this article. This article by Travers and Milgram references another article by Milgram. So this gives you a directed graph. Usually it's pointing into the past, but not always. Sometimes papers are published at the same time, so they point to each other. So the web is different. The web is continuously evolving, and the pointers are to current, most recent versions. Okay? So that's one precursor. Another precursor is encyclopedias. It used to be the case that encyclopedias were huge, heavy sets of books, not like the Encyclopedia Britannica, but they had huge cross-references. So each article references another article. So here, for example, there is a mathematician called John Forbes Nash. If you look at him in the encyclopedia, you'll get references to game theory, you get references to Nash equilibrium, which was defined and proved by him. You get references to RAND. This is a company that gets a lot of its money from the US military and does all kinds of war game simulations. You can see how it's going. All these articles are referring to related things. This is called associative memory. So a very important concept is that when you want to look something up, you look it up from what it talks about, not its address. Okay? It's not the book at the page 625 of the book. No, it's the chapter that talks about concurrency, for example. So you're looking up memory from the content. You're looking up articles that have certain content. This is called associative memory, content accessible. So it's like mental. It's like the way humans think. When I think of something, I can make a connection to something else in my mind, which is related, and my thoughts can wander, okay? This is also called a semantic network, where the nodes are concepts, and the edges are relationships. So you see, it's very abstract, in a sense, huh? So that's a precursor. But then there are some precursors that are much closer to the actual web. There's two articles that I want to bring out. They are both on the Moodle, and you should look at them. The first one is by Vannevar Bush. So this guy was a famous scientist before World War II. He was the national science advisor for the President of the United States. He was a visionary, but he also built computers. Most of them were mechanical computers. One of the computers he built, when someone described it, it sounds like a bunch of ladies knitting, you know, so that when it's running. So the guy was building these electromechanical computers, and he wrote this article in 1945, which basically predicts the web and browsers and associative memory. And he describes a device called the MEMICs, versions of human knowledge connected by associative links. Remember, it was written in 1945, but nothing like this existed. So some examples of what he said. The human mind operates by association. A MEMICS is a device in which an individual stores all his books, records, and communication, which is mechanized so that may be consulted with expedient speed and flexibility. Well, it sounds a lot like a browser search engine and my files. So this exists today. In those days, it was wild speculation. So the guy basically invented this in 1945. You see, he's very visionary. And people must have thought he was, I mean, come on, he was like science fiction or something. No way, okay? Not possible. It's too wild. But there's even better than that. This is Paul Auclair. This was in 1934. This is in French, but I will translate. So there's more, I give you a small piece of it. But he basically implemented a search engine using, the network was telegraph links, using telephone system. And the nodes were microfilm machines, where you could have a display and a keyboard, and you could bring up documents stored on microfilm. So the guy was one of the pioneers of microfilm in this first half of the 20th century. And he wrote a book called Le Livre sur le Livre, the book on the book. So he's basically, before World War II, so his goal was he was an idealist, a peace activist. One of his collaborators, I forget his name, actually won the Nobel Peace Prize. So he was in a really high community of people. And some of the things he wrote, just to show you what he wrote in 1934. So the universal book, it's formed by all the books. It's like an addition to your brain. The work table, the table where you work is not just, there's no books on it. Instead, there is a screen and a phone. Next, later far, there is a large building where it contains all the books and information which have been recorded at a distance or wireless, television or teletography. You can look at your Greek to see what he means by that. You can make appear on the screen the page that you read to know the answer to questions asked by phone with or wireless or with wire. So the guy has invented a search engine which answers questions as displaying them on a screen. You can imagine that? It's incredible, no? Nobody has ever seen that, And he imagined that in 1934, this guy. So this is just a small piece. You can see more on it. And he basically assumes you can have a keyboard and a screen and a network, And he actually implemented a search engine that worked by mail. You send questions to the library, and they will send you back. So the response time was kind of slow, but it was a search engine that distributed the system, okay? Unfortunately, all of he had big repositories were destroyed by the Nazis in World War II, unfortunately. So the guy, he was kind of unhappy at the end of his life. But you can see he's a visionary, huh? Universal dissemination of knowledge. So that was his goal. In 1934, he basically invented the web. Another thing that he invented, the words copy-paste, he was thinking of copy-paste in the early 1900s. So you can see, this guy, people must have thought he was crazy, right? To be thinking like that. Okay, so that gives you precursor. But there's a general lesson, huh? Old documents are very important. People tend to think that everything is on the internet. That is completely false. There is a huge amount of information that is not available on the internet and that is old. And so this guy is a visionary, okay? And Bonaparte Bush was a visionary, but they're not the only visionaries. There are other visionaries. Who knows what they imagined, okay? So looking at old stuff can be very, very fruitful, okay? So that was just a general list. But you can see that there was many precursors. This was already imagined almost 100 years ago, wasn't it? Okay? So the web came in 1990. This is 1934, so 55 years before the web, he had imagined it already. Okay? So let's talk a little bit now about the web itself. So it's a directed graph. Okay? Usually social networks are undirected. If I am friend, A is friend B, B is friend of A. If A is friends with B, A and B know each other. So typically, the friendship is undirected, but they're also directed network. So if A has heard of B, then there's an edge from A to B. That's directed, but B maybe never heard of A. So lots of people have heard of Barack Obama, but Obama is only one human. He doesn't know all these people. So information networks are usually directed. So we're going to go a little bit into directed graphs. A path from A to B is a sequence of nodes that starts to ends with B. Each pair is a directed edge. A directed graph is strongly connected if there's a path between any two nodes. Okay? Okay, so it's important now to study how big graphs are organized. Many big directed graphs are not strongly connected, but we can partition them into strongly connected components. So we can have a part of the graph which is strongly connected, and this part points to another part which is strongly connected, but there's no link back. Okay? So we can define a strongly connected component of a graph. It's a subset of the nodes. Each node has a path to each other subset, and the second condition is the subset is maximal. You cannot add any nodes to it without breaking the property. And you have to have these two, so it has to be maximal. And so any directed graph, big directed graph, arrows, can be translated into a directed graph acyclic, with no cycles, between the strongly connected components. So each strongly connected component is like one node in the translated graph. And that's an important way of looking at big directed graphs. Here's an example. So here's an example of a bunch of nodes. University of X, the classes, the networks. I teach at university, the class blog post, another blog post pointing to company Z. So it's basically a piece of the web, okay? It's a directed graph. We translate it, we convert it into acyclic graph, no cycles, between the strongly connected components. So for example, these four nodes make a strongly connected component because each node has a path to each other node. Between this one and this one, you go like this, for example. But it doesn't, you cannot add any nodes. So this is one strongly connected component. This bigger one is another one. Okay? Some of these single nodes are not containing cycles anywhere, so they are by themselves strongly connected components, vacuously, because there's no paths. And so here, each of the boxes with the dotted lines is like one node. Okay? You have to really understand that. One node is a strongly connected component, and then there's no cycles, or else it would be another strongly connected component. Okay, so that you have to understand. But once we get to that, we get to the bow tie structure. So this is really kind of interesting, because the web is not centrally controlled. Nobody controls it. Everybody just adds nodes the way they want. It's humans, psychology. So what is the global structure of this? Is it a mess? What is it? There's actually a very interesting structure. This was first done in around the year 2000, but this is still true today. So the numbers here are numbers from around the year 2000. So the web was already 10 years old then. So now the web is more than 30 years old. But it's the same structure, except the numbers are bigger. Okay? So how does it work? Well, there is one central, strongly connected component, a giant, strongly connected component. Remember, undirected graphs had the notion of a giant component? Well, here there's a giant, strongly connected component. So all the nodes are connected to each other here. And this one is very big. But then you have nodes that point into it, but nobody points back. And then you have nodes that the SCC points to them, but not back in. So you have a bunch of nodes funneling in, and then it also funnels out. So this is these two wings. In French you would say a nœud de papillon, a butterfly wing. You have these. In English, you would say bow tie. This is a bow tie. If you put it here, you have the left and the right parts, and then you have other weird parts, tendrils and tubes. So you could have a node here that connects to pages that end up nowhere, that don't go into there. So these are called tendrils. So the in part has tendrils sticking out, and the out part has tendrils going in. And then you can also have nodes, links, that go from in to out, but they don't touch the strongly connected component. These are called tubes. Okay. So how does the numbers work? Well, the biggest is this one. It's a little bit more than 1/4. Then this is like 1/4. That's 1/4. And all the junk outside is also like 1/4. You also have nodes, little pieces that are not connected, other components, small ones, 17 million. It's not so much. Most of them are part of this big structure. Okay? So this is the web as it was originally done, called Web 1.0, where the pages are basically documents pointing to other documents. But this was like around the year 2000. But since then, the web has increased in abstraction. And this is called Web 2.0. So this was the first decade of the 2000s. The abstraction level increased. So the original web was just text pages. I make a page, I link to another page. And the basic concept was a text page. And I keep adding pages. So that's a low level of abstraction. But in this decade, 3 things happened. Okay? First of all, instead of creating pages, organizations created content. So, which is many pages. So instead of creating one page, the university has a whole set of pages that are connected to each other, a subgraph. And I don't work on single pages, I work on a whole dynamic subgraph, shared content. Okay? So the creation is not pages anymore, it's whole subgraphs of related pages. So we're creating subgraphs now, much more than one page, and maintaining them. So that's the first thing. So the level is not just single pages, but it's subgraphs. The second is it's no longer people managing it. You have services. You have software managing the data. So people put data into databases or whatever, and then you have a piece of software taking the data out and creating web pages dynamically. And this is how part of the web is created. So people rarely, nowadays, sometimes they do, but the university does not create its pages manually. Most of them are created by software. Okay? So it's much more automated, so it's services. And the third thing is the owners. So the unit is no longer pages, it's people or organizations. But let's say people, so who own them. So a whole bunch of pages. You don't talk about pages, you talk about people or organizations. So somebody manages a blog. A blog is a whole collection of pages, a dynamic subgraph that is updated by some software, but that is owned by a single person or organization. Okay? So the connections between my blog and someone else's blog is not a connection between pages. It's a connection between people, the owners. It's more abstract, you see? It's not one page linking to another page. At the higher level, it's one blog linking to another blog, okay? So, some example. So, Wikipedia, a collaborative encyclopedia, which everybody knows. This is maintenance of shared content, dynamic subgraph, huge. Or Principle 2, Gmail, online email, online management email. All the pages are created dynamically here, okay? Principle 2. Principle 3, every person, if you have an account on Facebook, there's a whole bunch of web pages that you are owning because of that. And the more you are active, the more pages you have. So you have your own personal graph on Facebook. So that's Principle 3, okay? And there's also social phenomena. This is things we're going to study now in the course. First of all, software that gets better, the more people use it. This is called direct benefit. And it exists in the real world. The more people have used Word, Microsoft Word, the more useful the Word format. Okay, because I can send Word documents. So the use is improved when you have many people. Okay? This happens also on online services. For example, eBay. The more people that use it, the more people that put objects for sale, and the more people that buy objects, the more useful it is. Or recommendation systems. The more people that giving their opinions on movies, the more useful it becomes. And this is something we study later. It's called direct benefit cascades. And a second principle is called the wisdom of crowds. A group of people can be much smarter than one person. Not always, huh? If you have a mob, the January 6th mob, which stormed the Capitol, you could not say they were very smart. But the collaborative authorship on Wikipedia, they're all experts working together. The overall knowledge is very great. Or newspapers, or group evaluation of news content. So this can go in two directions. It can be much smarter, like Wikipedia, or it can be much more stupid because of cascades. So we're going to study that also in the course. Groups can become very stupid, and this is called network cascades on the network. You can have both smartness and stupidity. A third thing is called the long tail. Okay? You have most topics, people are not interested in that. I mean, most topics are very, very niche topics, like stamp collecting or Roman coins from the 1st century AD. Most people are not interested in that, okay? Or some dynasty, Tang Dynasty in China or something. Most people are not interested in that. But there's millions of these things that are niches. If you combine that all into one system, you get an enormous synergy. So the real world thing is like a supermarket. A supermarket, every single product, almost nobody is interested in it, okay? Who wants to buy a certain brand of toothpaste with mint and no sugar or something? I don't know. A few people. But the supermarket has 10,000 products. And it's because of that that it's popular. So this is called the long tail. This has a formal definition. It's connected to power laws. So the tail, the number of unpopular products is so large that together they're huge. This is why Amazon was so successful. And we will look at that. This is called rich get richer phenomena or power laws. So again, you can see that on the web. Okay. So now let's go on and to the real problem of the web, which is searching for information. And this is based on an idea called link analysis. So now we have a web with billions of pages, but I am one small human with small brain, okay? I cannot read 100 billion pages. How do I find things? This is called the problem of search, information retrieval. And it's hard. And there's many issues. Three important ones: inexpressiveness, synonymy, and polysemy. Inexpressiveness, if I want some very subtle idea, keywords are not good enough for this, okay? I want to understand the influence of Augustinian philosophy on Immanuel Kant. How do I find that? That's kind of very subtle. Another problem is synonymy, where multiple words for the same concept. In English, you can have scallions, but it's a kind of green onion, okay? There's many different kinds of shrimp. So prawns are a kind of shrimp. Okay, lobster is like a big kind of shrimp. So how do you do that if you have so many words? And then you have the opposite problem, where the same word has many meanings. Jaguar, what's a jaguar? Is it a car or an animal? Okay. There was also an operating system coming out of Apple that was called Jaguar. So what do we do? It used to be you had librarians who managed it. But now everybody is doing it. And the quantity is enormous. So you can't hire people, it's too much. And it's always changing. It's always changing. And very fast. Typical example, September 11, 2001, some big buildings in New York somehow collapsed, but if you typed World Trade Center in Google, you did not see that. You saw the building. It was too fast. So the problem is, it's called abundance problem. There's too much information. People are too rich. So how do you solve this? How can you find the right page? So this is a very important problem. And in 1990, people were really trying to find a solution. And the first ones found a good solution. became very rich, and all the other ones died. Have you ever heard of a browser called Alta Vista? Probably not. No. It was 1990. Or another one. Oh, I even forget the names. Okay. So Alta Vista was one of the browser, and it was a search engine with a browser. So this Alta Vista search engine, nobody knows about it now, because there was another search engine that took over, and that was enormously much better than Alta Vista, okay, which became Google. So how do you find a page? Cornell. Well, what is Cornell? Well, usually there's a university called Cornell University, so probably if you type Cornell, maybe you want the university, okay? How do you go to the page of Cornell's university? Okay. So how do we know that the word Cornell has to link to the university? Well, maybe there is a page which is at Cornell University, and it has many, many, many links. So there's the voting by inlinks. Maybe there's a page that has to do with Cornell, and there's a huge number of other pages pointing to it. So that's a good sign, right? The right page is important because other pages link to it. But that's not good enough, because sometimes pages have many links just because they're popular, not because they're relevant. So let me give an example. And this will lead us to PageRank. Okay? So let's count inlinks. Pages that are relevant to newspapers. Okay? The query newspapers. So here you have a bunch of web pages. Okay? And each one of them has pages pointing to it. And somehow they're all relevant to newspapers. So basically, we make kind of we filter pages. We keep the pages that are sort of relevant. And we look at how many links there are. So on the top, we have this one, which is the San Jose Mercury News, which is there because it's a newspaper that you can read in Silicon Valley. There's the Wall Street Journal, New York Times. But there's also Facebook, Yahoo, Amazon, which are not newspapers. Okay? So the New York Times gets a lot of votes. USA Today, it's a newspaper, gets a lot of votes. But Amazon also gets votes. Why? Because it's just popular. It kind of bulldozes everything. It's everywhere because it's so popular, even though it's not a newspaper. So it also gets 3 votes. But we want to remove this. It's not a newspaper. What can we do? There's actually a trick now we can use. We look at the network, and we don't just have newspapers. We also have pages that have lists of newspapers. So there's actually 2 kinds of pages. The newspapers and pages that point to newspapers. Okay? So we look at the network. So we go to the next step then. So we look at lists. So this is very common, right? On the web you can find pages that list things. Sometimes pages give lists of newspapers. Okay? Here are some good links to follow. Okay? So here, these pages on the left here we just showed pages with links that point to, well, let's take a look at these pages. Okay? Now we have the one on the top there with the number 8. This one points to 3 nodes that are maybe newspapers. But these nodes have inlinks, 2, 2, 4. Well, let's give a value to the list. See if we go backwards. Let's say, take a look at this one, which points at 3 newspapers. These newspapers have votes. Well, let's collect the number and put it here, 8. Okay? And the node that points to the Mercury News, Wall Street Journal, New York Times, USA Today has 11 votes. The node that points to Amazon and Yahoo has 6 votes, because here we have 3 and 3 in links. So we kind of take a step back. We look at the pages that link to the newspapers, and we sum all the inlinks to the pages they link to. Okay? So this gives numbers here, and the ones that have the highest numbers, let's say they're the best. Okay? So this one has 11 votes. So let's say, so it's better than this one, which has only 6, for example. Okay? So the pages score as a list is the sum of the votes for all the pages it links to. So 11 is 2 plus 4 plus, no, 2 plus 2 plus 4 plus 3. The 4 links. Okay? So that gives us a set of numbers for the lists. And now we can go forward again. So we went backward. Here we go from the arrowhead back to the links. Now go forward again. We make a new weight. Look at the San Jose Mercury News. It has a link from an 8 and from 11. So it has a score of 19. So you see we're kind of going back and forth now. We look at all the lists and see the pages they point to and collect all the inlinks. And then we go back, and this New York Times, for example, is pointed to by the 8, by the 11, by the 7, and by the 5. So if we add it all up, this gives us a new score. So we go forward again. So somehow we go backward and forward like this. And somehow if we keep doing that, we will kind of focus the search. Okay? So we go back and forth. Okay? A link from a best list, so this is the best list, counts more than a link from a list that's not so good, like this one. Okay? So we add it up. So we keep going back and forth. We find the pages with the most inlinks, votes. We find the best lists linked to them. We reweight these pages according to the lists, and then we keep going back and forth between the lists and the pages. Okay? So why are we doing this? Because this is kind of converging to the best lists and the best newspapers. Okay? So we normalize it. Okay? We normalize it because the numbers keep getting bigger. Let's normalize them so they're all the total sum is 1. Because otherwise they just keep getting bigger. So we normalize it. Okay, and keep improving. Okay, this is the final score. The limiting values. If we do this approach, somehow this actually gives better result than the just counting the inlinks. So you see the Mercury News is 0.199, Wall Street Journal 2, New York Times is 0.304, but Yahoo and Amazon has very little, because the pages that point to it are not really good pages. They're not giving lists of newspapers. They're just pointing to it, okay? Whereas the New York Times has only good pages pointing to it, pages with real lists. And this is kind of a recursive definition, okay? So the idea, so conceptually now, what did we do? We have two kinds of pages, which are called hubs and authorities. So we're looking at the web graph hub. Authority is the page we're looking for, a high-quality answer to our query. A hub is a page that has a list of pages we're looking for. So the authority is like a newspaper. A hub is a page listing newspapers. And each page has a score. How good is it? Authority of page and hub of page. And we have a technique now to compute the authority and hub values. So we start all the scores equal to 1, and now we will iterate. So the authority, the newspapers, we updated the sum of all the hub pages pointing to it. Okay? And now we update the hub is to be the sum of all the authority pages it points to. So it's kind of like this. Let me make a picture. So you have a bunch of pages which are hubs, and you have a bunch of pages which are the pages you're looking for, which are the authorities, and you have links going like this. And we start, and they can go from any of these to any of those. First of all, you update the authority to be the sum of the hubs pointing to it. So maybe this one has these two pointing to it, so you update this. And now we update the hub, so maybe the hub points like this. This one is taking the scores for this. So we calculate new hub, new authority. We go back and forth. Okay? Authority is good. So the intuition is the following. Authority is good if good hub pages are pointing to it. The newspaper is good if good newspaper lists are pointing to it. And a newspaper list, a hub, is good if it points to good newspapers. So it's a recursive definition. Each kind of node is good if the pointers to it are good. That's a recursive definition. And in order to compute it, we iterate until it converges. And we can show that it converges. And it's independent of the initial values. It's purely the structure of the network giving it to us. So here's our algorithm. And this one is already kind of getting to the direction of PageRank. So you have two arrays, auth of P and hub of P, which are huge, Maybe there's 10 billion pages. So auth of P is like 10 billion length array, and hub of P also. And now we iterate. We have an update step. The new value of authority P is the sum of all the hubs such that P prime points to P. The sum of the hubs pointing to P. Okay? And then the new hub is the sum of the authorities that P is pointing to. Do you understand this? The sum over P prime such that P points to P prime of authority of P prime. Okay? So this is like a calculation. And it uses the graph. You know the graph here. So it's a graph, a calculation on the graph. And then you normalize that because here the numbers are getting very big. So the authority of P is the authority divided by the sum of all authorities. This makes it so that they're normalized so that the sum is 1. And then you keep doing that, and eventually it converges. And the intuition is good authorities have good hubs pointing to them. And good hubs point to good authorities. And that's the condition. And you keep going. Okay? And this iterates. So this is very close to the PageRank invented by Google. And actually, this gives very good results. So to finish this kind of intuitive introduction, let me just introduce a little bit of PageRank, and then we'll talk more about it next week. So PageRank was a big thing, but theoretically it's not so complicated. So it was a key invention that led to the founding of Google. Google is rich because of that. It's funny how one algorithm can make a company so rich. And Larry Page and Sergey Brin, the two founders of Google, invented this algorithm. And this was the early 90s. It was like the Wild West. So I was already working in computer industry in these days. The beginning of the web. Ooh, people were making web pages in the early days. And there were search engines, many search engines, Alta Vista, Lycos, Webcaller, Yahoo, Ask Jeeves, and other ones. And so there was like a jungle of many search engines. And Google also was one of them. And the Google search engine has a button which is called I'm Feeling Lucky, which you may have seen. In those days it was they were very arrogant, they say. We really know. I'm Feeling Lucky would only give you one result, which is the top result of not just a whole bunch. And very often it was a good result. I'm feeling lucky. You click this, you will get only one result. And it was incredibly much better than all the competition because of PageRank. So all these search engines died, and Google eventually found out how to make money on their search engines using second price auctions. So the idea is if I'm searching for cancer, maybe it's because I have cancer and I want treatment. So you also get paid search engines. And how do you determine the value? Using auctions. And they make an enormous amount of money off of this, even today, off of this. And then all the rest is games for Google. They make Android, they make Gmail. That's just fun and games. They work in AI. But the real money maker for Google is the paid search. Okay. And how does it work? Using PageRank. So it's based on the hub and authority idea, but it's a little bit simpler. PageRank only has one value. You don't look at the authorities and the hubs pointing to them. Each page has only one number, which is somehow how important it is. If a page is a good newspaper, it also points to good newspapers. So the idea is that a page which is important by itself is also a good list of other pages. Okay? Important pages are pointed to by important pages, and important pages point to important pages. So there's an iterative algorithm. Okay? And let me just very quickly now end, and then we're done for today. So there's a really nice intuition that each page is like a bottle with liquid inside, and the liquid is how much liquid is how much importance. And the nodes are like bottles, containers, and the links are pipes. And the amount of fluid is constant. And so if a bottle is a web page, has 5 links out, the fluid separates into 5 pieces equal and moves to the bottles on the other side. So that's one iteration. So the fluid is circulating, and eventually it will concentrate on the important pages. Okay? And it works very simply. Okay? So the fluid amount is PageRank of P. Starts by being 1 over n. Everybody has equal. And then you compute the fluid on the outgoing links. So there's a link here from P to P prime. So the amount of fluid in page P divided by the number of outgoing links. So it's spread equally. And then the fluid is coming in. The new fluid is all the fluid coming on the in links from P prime to P. So the fluid is circulating like that. And eventually it converges. And the amount of fluid on each page is its importance. So simple. Okay? And that's where they make all their millions from. It's much simpler than general relativity. But Google made much more money than Albert Einstein. Funny, huh? Okay, let me stop there for today.